Chapter 8. Learning from Waste. If one used nothing, then one would waste nothing. That seems plain enough. But look at it from another angle. If we use nothing at all, is not then the waste total? Is it conservation or waste to withdraw a public resource wholly from use? If a man skimps himself through all the best years of his life in order to provide for his old age, has he conserved his resources, or has he wasted them? Has he been constructively or destructively thrifty? How are we to reckon waste? Usually we count waste in terms of materials. If a housewife buys twice as much food as her family eats and throws the rest away, she is considered wasteful. But on the other hand, is the housewife who gives her family only half enough to eat thrifty? Not at all. She is even more wasteful than the first housewife, for she is wasting human lives. She is withdrawing from her family the strength which they need to do their work in the world. Materials are less important than human beings, although we have not yet come quite around to thinking in that fashion. Once upon a time, society hung a man for stealing a loaf of bread. Now society treats such an offense differently. It takes that man, puts him in a prison, withdraws the benefit of an amount of labor which might make thousands of loaves of bread, and then actually feeds him many times as much bread as he stole. We not only waste this man's productive power, but also we call on our other producers to give up a part of their production to support him. That is flagrant waste. It is necessary, and will be necessary, to put men in jail until the news gets about that the profits of dishonesty do not compare with the profits of honesty. But there is no reason for thinking of a jail as a tomb for the living. Under first-class, non-political management, every jail in the country could be turned into an industrial unit, pay higher wages to the men than they could earn in outside industry, provide them with good food and reasonable hours of labor, and then turn over an excellent profit to the state. We already have prison labor, but most of it is ill-directed, degrading labor. A criminal is a non-producer, but when he has been caught and sentenced, it is very wasteful to continue him as a non-producer. He can surely be turned into a producer and probably into a man. Yet, because we value human time so lightly and materials so highly, we do not hear much about the waste of manpower in prisons, nor do we hear much of the terrible waste of withdrawing support from the families of the convicts and throwing them on the community. Conserving our natural resources by withdrawing them from use is not a service to the community. That is holding to the old theory that a thing is more important than a man. Our natural resources are ample for all our present needs. We do not have to bother about them as resources. What we do have to bother about is the waste of human labor. Take a vein of coal in a mine. As long as it remains in the mine, it is of no importance. But when a chunk of that coal has been mined and set down in Detroit, it becomes a thing of importance, because then it represents a certain amount of the labor of men used in its mining and transportation. If we waste that bit of coal, which is another way of saying if we do not put it to its full use, then we waste the time and energy of men. A man cannot be paid much for producing something which is to be wasted. My theory of waste goes back of the thing itself into the labor of producing it. We want to get full value out of labor so that we may be able to pay it full value. It is use, not conservation, that interests us. We want to use material to its utmost in order that the time of men may not be lost. Material costs nothing. It is of no account until it comes into the hands of management. Saving material because it is material, and saving material because it represents labor, might seem to amount to the same thing. But the approach makes a deal of difference. We will use material more carefully if we think of it as labor. For instance, we will not so lightly waste material simply because we can reclaim it, for salvage involves labor. The ideal is to have nothing to salvage. We have a large salvage department, which apparently earns for us $20 or more million a year. Something of it will be told later in this chapter, but as that department grew and became more important and more strikingly valuable, we began to ask ourselves, why should we have so much to salvage? Are we not giving more attention to reclaiming than to not wasting? And with that thought in mind, we set out to examine all our processes. A little of what we do in the way of saving manpower by extending machinery has already been told, and what we are doing with coal, wood, power, and transportation will be told in later chapters. This has to do only with what was waste. Our studies and investigations up to date have resulted in the saving of 80 million pounds of steel a year that formerly went into scrap and had to be reworked with the expenditure of labor. This amounts to about $3 million a year, or to put it in a better way, to the unnecessary labor on our scale of wages of upward of 2,000 men. And all of that saving was accomplished so simply that our present wonder is why we did not do it before. Here are a few examples. We formerly cut our crankcases out of trimmed steel plate, exactly the width and length of the case. That steel cost us 3.35 cents per pound because it had in it a good deal of labor. Now we buy an untrimmed sheet 150 inches long at 2.8 cents per pound, shear it to 109 inches, the sheared portion going to make another part, and on the remaining plate we can lay our 5 crankcases, which are cut in one operation. This saves 4 million pounds of steel scrap a year, and the whole saving amounts to nearly $500,000. The windshield bracket is somewhat irregularly shaped, and we formerly cut it from 18 by 32.5-inch rectangular steel sheets. A sheet gave us 6 brackets and a quantity of scrap. Now, by taking stock 15.5 by 32.5 inches, cut at a 7-degree angle, we get 6 windshield brackets as before, but also in the same operation we get 10 other blanks for small parts. This saves us 1.5 million pounds of steel a year. The oil can holder is in the shape of a cross, and we formerly stamped it out of steel with great waste at a cost of 6.35 cents each. Now we cut the 2 parts of the cross separately with almost no scrap and weld them together, and they now cost 4.78 cents each. The bushing on the steering gear, which is made of bronze, was formerly 0.128 inches thick. We found that it could be half as thick and do its work quite as well, which saves us 130,000 pounds of bronze a year, or more than $30,000. The headlamp bracket pad is a cross, measuring 7.5 by 3.5 inches, and we used to cut 14 of them out of a sheet of 6.5 by 35 inches. We reduced the size of the bracket to 7.5 by 3.5 inches, and now get the same number as before out of a sheet 5 7/8 by 35 inches, which saves more than 100,000 pounds of steel a year. We formerly cut the fan drive pulley out of new stock. Now we cut it out of the salvage from our hand door stock, which saves nearly 300,000 pounds of steel a year. By making very slight changes in 12 small brass items, we are saving nearly 500,000 pounds of brass a year. On 19 items, cut from bars or tubing we have, by changing the cutting tools and multiples and the length of the stock, save more than 1 million pounds of steel a year. For instance, on one part we used a bar 143 inches long and got 18 pieces per bar. We found that we could get the same number of pieces out of a bar 140 and 9/82 inches long, thus saving more than 2 inches per bar. On many small parts which were formerly cold rolled, we have changed to hot rolling. This, on 16 little items, saves about $300,000 a year. This general policy has been extended in a great number of directions. We found that in many plates and bars bought according to standard sizes or to specifications, we were not only paying for the shearing and the scrap at the steel mill, but were actually losing serviceable metal both in getting fewer parts out of the steel and also increasing our own scrap. Thus there was waste all around. We have been working on this only a year, and have hardly had a start on what can be done. Scrap, we take it, is something to be avoided, and not to be remelted until no other course remains. We had considered the worn steel rails from the railroad as scrap steel to be remelted, Now we pass them through a roll, which separates the head, the web, and the foot, which also gives us excellent steel bars which can be used for a number of purposes. This idea also is going to be carried further. On the other hand, such steel as we at present must consider as scrap amounts to 1,000 tons or more a day. And we had been selling this scrap to Pittsburgh and buying it back again as steel paying transportation charges both ways. Now we have erected at the River Rouge a series of electric furnaces and a large rolling mill, so that we can convert the scrap ourselves and save this item of double transportation. If we cannot avoid all of this scrap, and some of it is hardly avoidable, we can at least save the waste of human labor in handling and transportation. The salvage of materials about the shops has developed into a large industry, which is uncommonly important because it employs substandard men who could not work in production. We use these men, otherwise unemployable, to salvage the labor of other men. The simplification and classification of tools and machinery described in the last chapter have greatly aided in the salvage. Every part of an industry should fit into every other part. Thousands of broken tools and damaged plant equipment come in for reclamation every 24 hours. The value of the belting sent to the salvage department amounts to more than $1,000 a day. This is all repaired and reworked, the smaller scraps going to make life belts for window washers, or to the cobbler shop to be used for soles or patches. Broken tools of all kinds, pliers, wrenches, shears, braces, bits, hammers, drills, gauges, chucks, planes, saws, dies, jigs, and fixtures are repaired and returned to stock. And these repairs are not patchwork. The tools are actually rebuilt according to the original blueprint and come up to specifications in every particular. The department has a record of every machine operation in the industry and just what kind and size of tools are required. It can instantly tell what can be done with a damaged tool. Generally, it can be profitably reworked to a smaller size, there being several machines which can use a drill even less than an inch in length. If a drill or a broach or a reamer is worn out, it is cut down to a smaller size, always in accordance with the original blueprint. Cold-heading dies are all reworked to the next size, and so on down through the entire list of tools. All tool steel is classified and sorted before reworking. Tool handles of all kinds are salvaged. A broken shovel handle may make several screwdriver or chisel handles. Picks, rakes, spades, crowbars, mops, brooms, and similar implements are all salvaged as long as it is profitable. 2 men spend most of their time in repairing mop pails. Pipes, valves, joints, and other steam-fitting apparatus are reconditioned. Old paint is reclaimed to the extent of 500 gallons a day and is used for rough work. The salvage of oil and cutting compounds from steel shavings amounts to 2,100 gallons a day. Metal scrap, such as copper, brass, lead, aluminum, babbitt metal, solder, steel, and iron, are remelted. Since all our cast iron is classified under heads according to analysis, it is a simple matter to sort iron scrap and return it to the proper cupola for remelting. Molding sand is salvaged for its intrinsic value and because of the saving in freight and handling. Scrap oil is salvaged, and what is unfit for either lubrication or rust-proofing is burned as fuel. A process by which the cyanide used in heat treating can be diluted has been developed, and the cyanide bills cut in halves. The laboratories have developed a cement by which canvas facing may be stuck to pulleys, thereby reducing slippage of belts and the consequent waste of power. Old fire brick is broken up and reworked. Dross from the melting pots gives a yield. In the photographic department, the silver salts are recovered from the developing solutions, and the saving amounts to nearly $10,000 a year. The great amount of paper and rags gathered on a day throughout the plants bothered us, and so did the hardwood scrap from the body plant. Since we have swung over to all-steel bodies for most of our styles, the wood scrap has been much reduced. Having developed a salvage department, we at once start to make it unnecessary. The first thought with the hardwood scrap was to make it into paper, but we were told that only softwood could be used in paper making. But we went ahead with our plans for a mill and proved that it could be successfully done. The paper plant now uses 20 tons of scrap paper a day and produces 14 tons of binder board and 8 tons of special waterproof board, which is the result of a process developed in our laboratories. The board is of such great tensile strength that a 10-inch strip can bear the entire suspended weight of a Ford car. We use standard machinery with some improvements and adaptations of our own in order to make the process continuous and to cut down labor. Only 37 men are required to operate the mill, which contains more than 75 separate units of apparatus. Part of the product is used in backing the upholstery, and the remainder for containers in which to ship parts, which saves wood. The blast furnaces produce 500 tons of slag a day, 225 tons of which go into the making of cement, the rest being crushed for roads. The conversion of blast furnace slag into cement is quite common, but we could not afford to have the dust of the usual cement plant, and so we worked on a new process known as the wet, which is now being experimented with by other American manufacturers. As the molten slag runs from the blast furnace, it is met by a stream of cold water, which granulates it to the size of coarse salt. The wet mass, of which the wet slag comprises sometimes as much as 40%, though usually only 10 to 25%, is pumped through a 1,300-foot pipe to the cement plant, where it pours into constantly moving dewatering elevators, which permit all the water to be drained off before it reaches the belt conveyors at the top. These carry the granulated slag to the storage bins, from which it is drawn as needed. Inasmuch as this slag contains about 1% iron, the conveyors pass under powerful magnets, which pick up the iron particles, a considerable amount being recovered in a day. This is sent back to the blast furnace for reclamation. From the storage bins, the slag is carried to the mill, where, mixed with crushed limestone and 30% or more water, it is ground to powder. Before the mixture leaves the mill, it is so fine that 90% will pass through a 200-mesh screen. This mixture, of the consistency of cream, is called slurry and is forced by air pressure into huge storage vats. The analysis of this mixture is taken hourly, and corrections in the proportioning are made accordingly. The slurry then goes to rotary kilns 150 feet long, where, under intense heat, the cement is fused to clinker form, after which, with the addition of a small amount of gypsum, it is ground to powder, in which form it is ready for use. Gypsum is added to regulate the setting of the finished cement. The plant gives us about 2,000 barrels a day. We sell a little of it to our men for their own use, just so they can buy cement below the market price. The point, to repeat, in all of this, is the saving of human labor, so that it may be made more effective and more valuable. It was to save human labor that had gone into their making, that we brought 200 ships from the government. They had been built by the Emergency Fleet Corporation for use during the war, and there was no commercial demand for them. We are now breaking them up at our plant in Kearney, New Jersey. We can use some of the engines in our smaller plants, for many of the engines are first class. We do not expect to make any money out of the salvage of these ships. We did not go into it to make money. We simply did not like to see such a mass of fine material and so much labor go to waste when we might reclaim it. We bought with the wage, not the profit motive in our minds. Industry owes it to society to conserve material in every possible way, not only for the element of cost in the manufactured article, although that is important, but mostly for the conservation of those materials whose production and transportation are laying an increasing burden on society. As it is now, every manufacturing concern exists only to make its own products. It has not been linked up with the community. But it is becoming apparent that manufacturing concerns of size can be much more useful to the community than they now are, for example, in the matter of supplying fuel and power. Under the present system, coal hauled to a factory is just burned under its boilers, and a small fraction of its content utilized. Deliver 1,000 cars of coal to the shops of a great manufacturing district, and that is the end. In a time of coal shortage, the job of keeping the factories supplied with fuel and the job of keeping the homes supplied with fuel are distinct, requiring two great supplies of coal. Someday, in order to save human labor, we shall link all of this together. All phases of life should be and can be complementary.